Right, we're hopefully live. We did go live a little while ago for a short period, and then it went again. We didn't think we were on, but this time we do think it's working. So we're going to forge ahead and ignore that little bit of me just sort of rambling to myself a little while ago. Give me the email address again. It's contactscience@folkestoneacademy.com. I did say before, but don't know if you caught it, that we really do encourage you to email in any questions you have about the physics unit, so P1. So I can answer those live, or Miss Walker, who's on the email, can reply via email to you and answer those questions. I am just going to set up my timer. We are a bit late, but we're still going to do the set amount of time. So if you're watching it live, hopefully you can stay with us. If you're not watching it live, then it will still be about the same length of time, about half an hour, 40 minutes maybe, if we go over. But as I say, we're going to launch into it. Now, the PowerPoint should be available to you if you go to the Folkestone Academy Revision Science website, so you should be able to get that. But you will see it on here. Some of it though, some of the slides, I've put quite a lot of information on them for reasons I'll go into. It is quite hard to see. I've reused some of the PowerPoint from the 1.5 hour stream from last year, which I do encourage you to go and view. That was actually hosted by Mr. Pritchard, but he goes through a lot of the stuff as well that you need to know for this exam. So I'm just going to focus on the bits that didn't come up in so much detail last year that may well come up this year. So, without further ado, on to our P1 stuff. So, different types of energy you need to know about. Energy transfers, different stores of energy is all the first unit. I'm not going to go massively into it. You do need to be able to talk about energy stores and energy transfers. There's two potential energies that you need to know equations for. One is gravitational potential energy. That did come up last year. So did kinetic energy, calculated kinetic energy. You do need to know both of those. Those are energy stores you need to be able to calculate. But I'm not going to go through those equations because, as I say, they have come up and they are on the previous stream as well if you want to see those. I am going to show this one, which is a bit funny because this one is available on the equation sheet you get in the exams. You don't actually have to remember and recall this particular equation. You are given it. So elastic potential energy is equal to a half, or that can be put down as 0.5 multiplied by K. And K stands for the spring constant, which you should be given if you're expected to work out elastic potential energy. Otherwise, they could get you to rearrange it to calculate the spring constant, but assuming you want to get the elastic potential energy, you'll need to be given the spring constant. And then E stands for the extension. So what that means is if I take a spring or a rubber band and I extend it by stretching it out, it will store elastic potential energy, and that energy I'll be able to calculate using this equation. But this one is given to you on the equation sheet. Another little tip with this equation though, and I will just say this, is if you can't remember the equation for kinetic energy, you can use this equation, because kinetic energy is equal to a half, or 0.5, multiplied by the mass of the object that you're trying to work out the kinetic energy for, times the velocity squared. So it's very similar to this one. Now you're given this one, you're not given that one, but if you can use this one to turn it into that essentially, you've got both of them, 2 for 1 if you like, and that equation is given to you. The reason I go on about this one is because I do imagine something will come up about springs or elastic potential energy, because we didn't have it last year. Work done, energy transfer. So work done and energy transfer are essentially the same thing. When you do work, you transfer energy, or when an object does work, it transfers energy. It only actually happens, energy is only transferred or work is actually done when an object is moved a distance. And the force required to move that object, measured in newtons, if you multiply it by the distance that object has travelled in metres, you can calculate the work done. Now work done and energy transfer are a type of energy, so therefore they are both measured in joules. I will go into it a bit later, but I've talked about it a lot in lessons, in these streams already, the previous one I did, that they do like that, giving you numbers in the incorrect units and then getting you to convert them. So they might get you to work out work done in joules, and then it'll ask for the answer in kilojoules. so they'll get you to convert it. So if you've got an answer in joules and you want to convert it to kilojoules, you need to divide it by 1,000. But I do come into some of that a bit later. Anyway, equation for work done is force multiplied by the distance travelled by an object. And then also power as well. Power is linked to that. How powerful a person is or an object is actually how quickly they can transfer energy or do work. So there are two equations which are essentially the same thing for power. Power is work done divided by the time taken for that work to be done. Or it can be energy transferred divided by the time taken. Both of these are essentially the same, measured in joules, divided by the time in seconds. Now again, I'll talk about that a bit later, but the time needs to be in seconds. They are likely to give you a time not in seconds, in minutes or hours, and you need to convert it to seconds to do all these equations that you need to do. If you didn't know already, physics is clearly very maths heavy. There's the equations you've got to remember for the exam. You do get extra equations on an equation sheet which will be available to you. The equation sheet is the same for P1 as it is for P2. Looks a little bit something like this. So it has several equations on it, 7 equations in fact, but a couple of them are only used in the higher paper and 5 of them used in foundation. Several of them come up in P1 and they all technically can come up in P2 as well. Another equation, but this one again is on the equation sheet, but you need to know how to use it, what these different symbols mean, is force-specific heat capacity. For this, it is changing thermal energy. Thermal energy is obviously our heat energy, our internal energy as it is now. So if you want to work out the energy or change in energy of a material when it has changed its temperature, you need to know the mass of that material, the specific heat capacity of that material. Now this will be given, or you could be expected to work it out in a required practical, which I'm going to talk about next. But if we're talking about water, it's given as 4,200 joules per kilogram per degree Celsius. And the change in temperature. So change in temperature will be the difference between the final temperature and the initial temperature. If they don't give you it, expect you to work it out, or they could just give you the change in temperature right away. So change in thermal energy is equal to the mass of the substance multiplied by the specific heat capacity of the substance times the change in temperature of that substance. As I say, this equation is one of the ones given to you on the equation sheet. You don't have to remember it, but you do have to be able to apply it. The reason I talk about that equation is because this is a required practical. This one did not come up last year. Now I did say that there is quite a lot of information on some of these slides, and you possibly can't read that on the screen, particularly if you're watching it on a phone. Don't worry too much about that. Hopefully you can have access to this or gain access to this and actually look at the slides yourself. But I wanted to put it up there because this is the method for doing this practical. In case they ask you a 6-mark question where you have to talk about this practical. I'm going to go over it briefly though as well, and I don't actually like this one. There's quite a few steps to it, there's quite a few things to do with it. Makes it quite a challenging practical. What we've got here is our diagram of the setup. Now you should have done this practical and hopefully you remember it, but it may well have been in year 9, so a few years ago. You take a block of material. The most common one we use is copper. So you take a piece of copper, a block of copper. And the copper has 2 holes in the top. In one of the holes you put an immersion heater, which is essentially an electric heater. You place it into one of the holes. You then place a thermometer into the second hole. Now around that thermometer you can put a piece of petroleum jelly, which is just like that gel stuff, like Vaseline essentially. You can put onto your thermometer. And that's to place it in contact with the metal cube itself, or metal block itself. You can also, another alternative is to fill that little gap with water. So to place water in it so the thermometer is in the water. Now that's to create the contact to transfer the energy from the cube or the block itself to the thermometer. Your immersion heater, your electric heater, will have a voltmeter and an ammeter attached to a power supply. You need to insulate the block, so you're going to put some sort of insulation around the block. Quite often when this is done in a classroom, it's done inside a plastic beaker with cotton wool wrapped around the block. That's to prevent the block losing heat to the surroundings. Again, just like in chemistry with the exo and endothermic reactions, the number one source of error in these experiments is where the block loses its heat to the surroundings and therefore doesn't heat up as much as we would expect. So heat loss to the surroundings. To combat that, you insulate the block. So we've got our block of copper, which we need to take the mass of in kilograms. We need to take the mass of that block in kilograms so we can use it later on. We then set up our circuit, place our heater in, place our thermometer in, and then we turn on the power pack. We need to take the recordings on the voltmeter and the ammeter, and it's suggested that for every minute, every 60 seconds, you take the temperature rise. So how much is the temperature increased by? You're interested in how much the temperature is going up. So the temperature rise, the change in temperature. So you need to see where it starts and see how much it goes up every sort of minute for up to 10 minutes is what they suggest. You're going to record your results in a table much like this, but you need energy transferred, and this is where this practical gets tricky because you need the energy transferred in joules. So you actually have to calculate it. You can't get that directly from this experiment. The way we do that is we actually have to use some equations, and I will come back to these equations, but just ever so quickly to tell you those equations. The first one you're going to need is power. You need the power of the device, and that is the voltage or potential difference multiplied by the current, which you will have recorded during the experiment. These shouldn't change as the experiment goes on, so you just need to record them once and check that they've stayed the same. Once you have the power, you can work out the energy transferred, and that's what you need to put into your table here. So you can put that into your table. So energy transferred, again, as I say, you need to use a couple of equations. It's why this practical is a bit tricky. Is equal to the power multiplied by the time in seconds that the experiment's been running. So once you know your power from your voltage and your current, you can work out the energy transfer from the power multiplied by the time, and you can get that. Once you have those results, there's two things you can do. You can plot that into a graph. So you can plot that into a graph, and you can actually work out the gradient of that graph is actually equal to, it's a bit weird, but the specific heat capacity can be found. I'm going to write SHC for the specific heat capacity, can be found by doing 1 over the mass times the gradient of the line. Now by gradient I mean the slope of the line on the graph that you plotted from this data. As I say, it's a pretty nasty practical because there's all of that to go through to get the results, but that's an overview of how it works. You can, another way, get the specific heat capacity directly by going back to this equation. If you just do it after, say, 10 minutes, you should know the energy transferred by doing the power multiplied by your 10 minutes. You should know the mass of the copper block because you took the mass at the start, which could also be used here. And you should know the change in temperature after 10 minutes. So you're going to have to rearrange this to get the specific heat capacity. And you do that by doing the change in energy, or energy transferred, divided by the mass times the change in temperature. As I say, it's a pretty tricky experiment to go through, but it is one of the required practicals. You can alter this experiment, so you can do it for different blocks. So you could do copper, you could do aluminium, you could do different metals, and you could actually find out the specific heat capacity of each one using this experiment. Still talking about energy transfers. Most energy transfers, in fact, I say most, let's just say all energy transfers, are inefficient. They don't transfer all the energy from one store to another. And that can be represented in a few ways. Now, they used to favour these things called Sankey diagrams. Now, they may not come up now, but they still can be used to show the energy involved in a transfer. This one in particular is for a child on a slide. This is their gravitational potential energy at the top of the slide. So when they're at the top of the slide, they have 1,200 joules of energy stored in them. The child then goes down the slide and they convert 800 joules of that to kinetic energy, making them go fast down the slide. That's what we want, because that's the thrill of a slide, going faster. But unfortunately, because there is friction with the surface of the slide itself, they are transferred also as internal energy, which is thermal energy, essentially, the new sort of term for it. So internal energy of the slide and the child. Both the slide and the child will warm up slightly as the friction when you go down the slide. It's created, that's 400 joules that is lost via that. So that actually slows them down, because less of this energy is transferred to kinetic energy, so they go slower. So a Sankey diagram represents that energy transfer, and usually this shows the energy that's being used, and this shows the energy that's being lost. As I said, very few energy transfers are 100% efficient. In fact, pretty much no energy transfers are 100% efficient. The wasted energy is usually spread out for internal energy, emitted via light radiation, sound radiation, thermal radiation, or infrared radiation if we want to be technical. But you can actually work out the efficiency of a device using this equation. So the efficiency is equal to the useful energy out, which in this case is 800 joules, divided by the total energy in, which is 1,200 joules. Now it can just be left as that. You can have efficiency, which should come out as a decimal. Efficiency, if you're doing it just by doing that, will work out as a number less than 1. But sometimes you can convert it to a percentage as well. And all you need to do at the end, if you want a percentage, is times it by 100. Now again, if you do that, useful energy out, 800, divided by total energy in, 1,200, times by 100, you will get an efficiency less than 100%. Okay? Because energy is wasted or dissipated through internal energy loss. I'm not going to go into detail, but you do have to look at ways of reducing energy dissipation. And that, in this case, what you would want to do is you'd want to reduce friction. Now, for a child on a slide, that could be wearing a different material clothes to reduce friction. But essentially, they often talk about 2 ways to reduce energy loss. If you're talking about friction, generally they talk about lubrication of machinery or parts to ensure that friction is reduced, so they slide over each other easily and less friction is affected or energy is lost through friction. And if they're talking about, say, a house, they could talk about a house losing energy. They could talk about insulation, thermal insulation, so insulating a material to reduce energy loss. They did have a question on last year's higher paper, I believe, about cavity wall insulation, reducing thermal conductivity, so therefore reducing energy lost. Electric current. So electrical circuits is a massive topic along with energy, but didn't come up too much last year. There's a few key areas I want to focus on. It certainly didn't come up very much at all in foundation. It came up a little bit in higher. Again, it's just my prediction based on just looking at the papers and cannot guarantee anything. I feel that electrical circuits, electrical current, electrical calculations could be a much bigger topic this year. So I'm going to do a bit of time on it and focus on it a little bit. First of all, what is electrical current? Well, electrical current is the flow of charge, and charge is caused by the movement of electrons. That can be in simple circuit components, and you need to be able to know your circuit symbols and draw some simple circuits. I'm not going to go through all the circuit symbols now. They're easily found in any revision guide or on BBC Bite Size, but you do need to know your different circuit symbols. These are key equations that come up a lot when dealing with electricity. So you've got charge, which symbol is given Q for charge, is equal to current, and the symbol for current is I, strangely enough, multiplied by time. Okay, so charge is equal to current multiplied by time. I will go into the units of these in a second, but essentially that's your equation, not given on the equation sheet. Charge is equal to current multiplied by time. A really crucial one is potential difference is equal to current multiplied by resistance. Potential difference current times resistance. V equals IR, a fundamental of electricity. And then when we're talking about electrical power, we've already talked about power in the sense of energy transferred divided by time. you can work out electrical power, because a lot of things when you're talking about power, you're talking about electrical devices. What is the power of that electrical device? And to work that out, you can do the potential difference multiplied by the current. Now I will show you one more equation that you need to know as well that I haven't put on the slide, and it's quite a clever one you can derive. If you know these other ones, you can work out this final equation. It's another equation for power. The way it works is this. So power, we know, is equal to V times I. That's right there. So we've got that one. But we also know that V is equal to, so potential difference is equal to the current times resistance. So we can put it into this equation as well. So if we change that for current times resistance times I. Now when things are multiplied together, it doesn't matter the order. So these brackets are kind of irrelevant, and we can just put all the terms together. So it actually comes out as power, which I'm going to leave as P, is equal to I squared times R. And that's another equation you can be asked to use for power as well. If you're not given the potential difference, but you need the power, you can do it by doing the current squared times the resistance of the device, component or circuit. As I said, I was going to talk a bit about units and symbols for different things. I've already talked about charge. It's given the symbol Q, strangely enough, and it's measured in coulombs.